Hey guys, I'm Jordan Stovik, and today I'm going to be talking to you about these PEGDA PC cantilevers. Basically, the use that they were looking for these are an application called biohybrid actuators, where you take a synthetic material, such as this cantilever, you seed it with like heart cells, later on, these heart cells that contract on their own and beat on their own, and you can construct them in ways that create a certain movement. So one of the things that they were looking into is past studies had used stiffer material like silicon to create the base synthetic structure, and because of the high elastic modulus of that structure, the beating was not regular. It was very low frequency and not very effective. So they were trying to use these hydrogels that have a lower elastic modulus, about 20 kilopascals, and it would allow for they thought it would allow for a better contraction and more displacement, basically. All right. So the paper is multi-material biofabrication of hydrogel cantilevers and actuators with stereolithography. So we're using stereolithography again, like we have in most of the studies we've been talking about this time. It was written in Lab Chip 2012, Volume 12. And it discussed the use of stereolithography to create these biohybrid actuators like I was talking about. And the main question was, can SLA and PEGDA PC be used to create flexible biohybrid actuators? So PEGDA PC is a combination of this acrylic PEG collagen and polyethylene glycol diacrylate. Basically, they use these two combinations because the PEGDA has the elastic modulus and the mechanical properties they're looking for in these biohybrid actuators, and the acrylic PEG collagen, which is PC, has properties that allow the cells to basically facilitates them a little bit better and makes them a bit better for the cells to stay on the structure. And the cardiomyocyte tissue, which is just the heart tissue taken from neonatal rats, they seeded it on the top side of these flat cantilevers at top. These are PEGDA PC 700, which has to do with the molecular weight. Those ones have a stiffer modulus of about 250 kilopascals, whereas this 3400 right here has an elastic modulus of about 25 kilopascals. And that's one of the reasons you see this bending. It's partially because this is also very hydrophilic substance. So it absorbs water, and when it absorbs water, it sort of warps the shape of the substance. So they had to account for that in their geometries that they were using for SLA. And the things that the main focuses that I saw were examined were the cantilever bending due to the cell traction, which is in the first 24 hours after the cells were seeded, where they're sort of connecting with each other and forming their tissue film, and the final cell actuation and force over time. The tools that they used for this were a Sony Handycam, really high technology stuff there, and this anti-sarcomeric alpha-actinin and anti-DNA, which you can't really see on the bottom of the screen there. That wasn't used too much to talk about these, but they use it in these images here, which this is the 700 right here and the 3400 here. This elongated shape is supposed to allow for better muscle action and contraction during their life cycle. So our first question is, would the cantilevers bend due to the initial cell traction? And you saw this image before, and this cantilever up here did not bend because of its high elastic modulus, so it stayed just about the same. And you can't really tell on this graph. There's a slight line right there for the angle on this cantilever, but then you've got the high bending in this, and over time, as you can see from left to right, the angle sort of came down as the cells were gaining traction and connecting with each other, and you can see that in this plot as well. And so it ended up decreasing by about 23 degrees due to cell traction forces, which is sort of what they're looking for. They want the cells to be able to move this thing, because that's the whole point of the entire biohybrid actuator. The next question is, what actuation forces are present in the seeded cantilevers? And first, we have to look at whether they are actuating. So in the first 24 hours, which is this small line here, there's no actuation in either the 700 or the 3400. And then over time, they after 2 days, they shot up on this 3400. Every single cantilever they had 4 cantilevers that were the 3400 series were actuating, and then it stayed at 100% for the next day too. And the PEGDA is about 25% on the first day, on the second day, I believe, and then about just a little bit over 80% were actuating after that. And so it showed that like the lower elastic modulus allowed for a easier actuation in the material itself. And here's the beating frequency. So since these are hard cells, they're going to beat on a certain pace. The stiffer elastic modulus of the 700 sort of inhibited their beating, so it was only about 0.5 hertz, something around 1 beat every 2 seconds. Whereas with the more flexible 3400 series, you got about 1.2 to 1.4 hertz, depending as time went on, and that sort of shows that these muscles are better suited to work with this lower elastic modulus. And then we got to look at the actual forces. So here's the displacements for each beat up here as the days were going on, and so it's around 200 microns on the third day here, up to about 400 microns right here. So, and this is obviously for the more flexible series, whereas the other one barely beat at all down here. These graphs really were kind of poorly put together. They were supposed to compare them, but when you've got almost no displacement or very small displacement, it doesn't really change over the bottom of the graph here. And then they measured the two forces here as well using finite element analysis, where they took the displacements and put them on a model and checked them with beam calculations as well. And you've got about 0.89 micronewtons for the 700 series, so there's not a whole lot of force there compared to the 5.09 micronewtons for the 3400 series. So it shows that these muscles tend to work better with this more flexible material, and you could use them for a better application using that material. So the key conclusions are the flexibility of the 3400 series cantilevers encourage a higher actuation force and more frequent actuation force from these cardiomyocyte cells. These higher forces and frequencies can also be controlled chemically and allow for a greater application in these biohybrid actuators than with the current silicon materials and other research they had done. My personal critique of this paper, it was very well documented, and they had references to past research to sort of explain where their hypotheses came from and their different theories. And the only thing that they lacked insight was into sort of the use of these biohybrid actuators. They talked about making them swim or pump or walk, as they called it, but they didn't really say what that would be used for, and I didn't really know that.